In this presentation, Fluxtrol intern Alec Williamson from the Colorado School of Mines explores how induction heating can be used to replace traditional gas-fired furnaces in steel manufacturing. The research focuses on rapid heating techniques to enhance the properties of advanced high-strength steels critical for applications like automotive manufacturing. Alec explains how this electrified approach can reduce carbon emissions, improve steel performance, and increase production efficiency, offering a more sustainable future for the steel industry.
Hi, I'm Alec Williamson. I'm going to be talking about Project on Advancing Induction Heating Technology for Sustainable Processing and Property Enhancement for Advanced High-Strength Sheet Steels. And this project is supported by the AIST Sustainable Technologies for Steel Manufacturing Program. My advisors on the project are Dr. Lawrence Cho and Dr. Emmanuel Moore from the Colorado School of Mines Advanced Steel Processing and Products Research Center. And our advisors are from US Steel, Cleveland Cliffs, and Rob from Fluxtrol, supporting us through AIST as well as FEES. And there have been additional undergraduate participants on the project as well. Sam Finley, David Ulrich, and the senior design team, Dominic Cohen, Sam Nicolai, Colton Brown, and Marty Martin. So the project objectives were primarily to advance electrified induction heating for sustainable steel processing and to explore the feasibility of using induction heating in replacing conventional gas-fired furnaces throughout continuous annealing lines with the potential to enhance steel performance, specifically looking at rapid induction heating applications to advance high-strength steels. And computational laboratory induction simulations were conducted along with student engagement in the steel industry remaining a high priority in the project. For some background on industrial electrification, the U.S. Department of Energy laid out a roadmap by 2050 to achieve net zero carbon emissions, and industrial electrification is a major component to this roadmap. The U.S. steel industry makes up more than 7% of the total global CO2 emissions, and 2/3 of steel is already made using EAF technology, so there's limited opportunity for further implementation of EAFs to reduce this carbon emissions. Industrial electrification is a major avenue that could be used to reach this. So continuous annealing lines in general offer a lot of advantage in electrification, as there's not only the component of reducing gas-fired furnaces, but also the ability to control microstructure and property processing relationships. So direct fire furnaces are currently used throughout continuous annealing line. The schematic is shown below with burners and radiant tube furnaces. And this project really seeks to explore the possibility of using induction coils to replicate the direct fire furnaces and electrified radiant tube furnaces for those gas-fired radiant tube furnaces. Some of the key challenges and opportunities in this project are optimizing a lot of the microstructure processing property relationships for the various steel grades being produced on strip mills currently. And there's an increased emphasis on initial microstructure, especially the cold roll condition when looking at rapid heating in these steels. Additionally, the processing operation maintenance parameters will need to change significantly with rapid heating, and there's different processing windows and routes and additional flexibility considerations, along with different magnetic permeability using induction heating and energy input. So you get to consider the different efficiencies of coil geometry and other such things. Additionally, temperature uniformity has been a major concern with different types of induction heating in strip production, and temperature measurement and control would need to be implemented to ensure that you're having homogeneous heating throughout the strip. Additionally, the cost of electricity relative to the cost of natural gas is an important consideration. And then further considerations this project doesn't really explore is the surface quality control aspect, where scale reduction, selective oxidation on coated and uncoated products needs to be considered for hot dip galvanization, for example. And reoptimizing gas atmosphere conditions might allow some interesting opportunities for enhancing this process. The as-received microstructures used in this project will represent steel received from POSCO, and the cold roll conditions consist of perlite and martensite along with fine cementite. The Vickers hardnesses were around 370 with tolerance of 4.5 for the 3 manganese alloy, and additional the alloys considered were 3 and 5 weight % manganese alloys with silicon and chromium additions. So in conducting this project, we really sought to design conventional rapid and ultra-rapid cycles that first off could replicate the current conventional annealing line practice for QNP. The conventional practice, we established a lot of our parameters by talking with industry on what they currently do and what would be suitable for this alloy. We used dilatometry to obtain the critical temperatures used, and Next, move to rapid cycle, where we employed rapid heating and faster cooling rate for some flash annealing benefit. Again, the critical temperatures were obtained using dilatometry, and an equivalent partitioning step was used. And lastly, with the ultra rapid cycle, we employed a much shorter partitioning time and used an equivalent diffusion calculation to approximate an equivalent carbon diffusion in the stage. And when we conducted these cycles using dilatometry, we were able to obtain the secondary martensite start temperature from the final quench of the curve. So on the left, these curves show the relative change in length of the sample as a function of the temperature during heating. And upon final cooling, that deviation linearity shows that formation of secondary martensite. And this is really important, as secondary martensite is a really brittle phase that's untempered and cause very undesirable mechanical behavior. And we saw that there was a lowered secondary martensite start temperature for the rapid cycle as opposed to the conventional. Additionally, secondary martensite start temperature was observed to decrease with decreasing quench temperature, as shown in this plot here. And the secondary martensite formation was observed to be lower with conventional when compared to the rapid cycle. And in this project, we wanted to predict the retained austenite fraction stabilized through the QMP heat treatment process. And this figure here shows the model proposed by Spear using the Koisted-Marburger equation to predict the transformation of martensite, and assumes full partitioning of carbon and suppression of carbide and bainite formation. And surprisingly, with our MSAT results on dilatometry tested specimens, we were able to observe very similar characteristic mountain shape profiles, and additionally an enhancement in the retained austenite fraction stabilized using the rapid conditions when compared to the conventional. Additionally, we observed very similar retained austenite fraction stabilized using the ultra rapid cycle, with some exception in the 5 manganese ultra rapid cycle with the peak conditions, but largely consistent with the 3 manganese condition. And this is really significant, as the enhancement in retained austenite allows for better mechanical performance through the trip mechanism. When we look at the microstructures for the peak conditions for the 3 manganese alloy, or quench temperature max condition, we can see on the right, on the top, we have the rapid condition micrograph, and the bottom we have the conventional. And through this, we can see there's a clear difference in the not only martensite packet size through grain refinement, but also there's a finer carbide distribution in these kind of line features shown here that are indicative of possibly undissolved cementite from our initial SRC microstructure. When we look at the adjacent conditions, the 160 degrees C and 200 degrees C conditions, we see largely consistent results where a lot of these line features are persisting in the rapid condition and not so much in the conventional. And we're also seeing much larger martensite packets, indicative of less of a grain size refinement effect. When looking at the 5 manganese condition, again, this is largely consistent behavior throughout these samples, as the rapid condition shown above has these much better preserved line features from the as received condition, whereas only faintly in the conventional shown below. And again, when looking at the adjacent conditions, again, we're showing that this is largely a consistent phenomenon throughout the specimens tested. The retained austenite morphology, the conventional and rapid cycles, was tested using backscatter diffraction and inverse pole figure of the retained austenite indexing grains was overlaid on top of the grain boundaries, the prior austenite grain boundaries, in order to show the retained austenite morphology, where the white colored grains are assumed to be martensite, and these colored regions are retained austenite with the pole figures down below. And as you can see with the conventional, we're seeing much larger blocky retained austenite features as opposed to the rapid shown below over here. This is largely due to the difference in the retained austenite morphology that's going to be stabilized. In literature, it's pretty documented that thin film morphology is promoted with rapid heating, and therefore we're seeing very different morphology stabilized. And this could be the reason we're seeing a decrease fraction predicted by our scan, whereas our MSAT, which is able to observe the bulk retained austenite fraction through magnetic testing, is able to pick up on this higher fraction stabilized in the rapid condition, whereas EBSD is really only going to show us these blocky features that are more prevalent in the conventional. In conducting our tensile testing for this project, we needed to study the thermal gradients from Weeble heat treatment, and hardness testing across the original gauge length suggested that we needed about a 32.6% reduction in the load-bearing capacity in order to fail in an effective gauge length that would be uniformly heat treated. So looking at these thermal gradients, we can see that past the 5mm offset, we're starting to see a pretty pronounced drop off in that uniformity, which is pretty significant when we're failing in a region that has a different quench temperature than we really want to study. So we decreased the load-bearing area by 40% in the central 10 millimeters in order to characterize the tensile properties in the region that would be uniformly treated. And when testing these specimens, we were able to see largely consistent tensile behavior where the yield strength was largely preserved across rapid and conventional cycles, and the ultimate tensile strength behavior was largely similar. And there's also a possible enhancement in the elongation from the rapid condition using the 3-manganese alloy. Cycles did fail prematurely in the 5-manganese due to possibly some secondary martensite presence. And these cycles, it's important to note, were designed for replicating the conventional parameters and stabilizing an equivalent QMP cycle, and not necessarily for property enhancement. So the fact that we're seeing a possible increase in the elongation and largely consistent tensile properties is very successful within the scope of the project. In electrifying current lines, there's been some discussion around the existence of current lines having relatively fixed parameters and line sizes, and so computational Alta simulations were conducted for multi-state strip heating to determine optimal induction processes for heating in current lines, and the thermal and electric efficiency during the stage heating was investigated for both longitudinal and transverse flux. And there was a significant efficiency benefit to heating with transverse flux at and above the Curie temperature, and with structures that had starting retained austenite. And shown here is a schematic of a cycle that might be implemented in electrifying a current line where longitudinal heating could be used during the initial heating stage, heating much more rapidly all the way to around the Curie temperature, and then past the Curie temperature into the austenitization regime. You can employ step heating using transverse coils to have a high degree of efficiency. When looking at the Alta simulation conducted for energy efficiency in strip production, we examined the impact of switching from a longitudinal flux coil to transverse flux, looking at exclusively a martensite starting microstructure in this case scenario, where the power total and the electrical efficiencies are primarily of interest in this study, where we can see much better electrical efficiency shown using the transverse flux at and above the Curie temperature when compared to longitudinal flux for the same temperature regimes. And by comparison, when we look at the transition from longitudinal to transverse for martensite starting versus martensite and starting austenite structure, we can see that the transverse flux is able to heat very efficiently. We can see that there's largely not a huge efficiency hit in starting with 15% austenite when compared to a martensite starting structure using transverse flux. Overall, there's a similar energy efficiency, except for that initial stage of heating where you do see some bump when starting with around 15% austenite. And we'd also like to investigate the energy efficiency of the ultra-rapid cycle in future reporting periods. In conclusion, the project explores the feasibility of using induction heating to partially entirely replace conventional gas-fired furnaces and continuous annealing lines, with a focus on rapid induction heating applications to advance high-strength steel. QMP involving rapid induction heating stabilizes higher fractions of retained austenite compared to conventionally continuous annealed microstructures. Additionally, rapid heating can result in finer distributions of retained austenite due to the development of inhomogeneous microstructure, and rapid partitioning effectively stabilizes similar fractions of retained austenite. In future work, we'd like to conduct additional tensile testing for lower quench temperature samples, evaluate total elongation, and perform EBSD on the ultra-rapid conditions to assess additional retained austenite morphology, and also perform ultra-rapid partitioning cycles for 1 to 3 seconds to assess sensitivity and possibly some hardness data as well. I'd also like to acknowledge the support provided to us by our sponsors and from other undergraduates who have contributed to the project. Thank you.